Hi, welcome to GovCIO Media and Research's Federal IT Efficiency Summit. I'm Jordan McDonald, staff writer with GovCIO Media and Research. And today, we're joined by Alan Hope, head of the Mission Development Branch at the Naval Research Laboratory. Alan, thanks so much for joining us.
You're welcome. Glad to be here.
Alan, you've got a really important and interesting purview, but I don't think a lot of people understand it. Could you help me get a grasp on the importance of maritime domain awareness, MDA, in the digital age?
So in the digital age, right, it's all about information, and maritime environment is extremely rich and data-driven. There's a lot of systems that are there to ensure safety of navigation of the seas, like AIS, and there's also bad actors that are doing things to deny that. So the hard part of the problem is really putting together all of the digital tools we have, whether that's electro-optical imagery, SIGINT information, ELINT information, this AIS information, and anything else that we have that lets us know things about where ships are, where they're going, what's on them, who's on them, and put that all together in a nice, neat wrapper so that analysts can understand it, right? So it's not just about the data. It's assembling the data in a fashion almost like an object-oriented problem. Like if you had the good ship Lollipop and an analyst wants to know about that, you want to know when it was built, when it was operated, where its last ports of call were, where it's headed to next, what its cargo is, what its crew is, and all those things. So associating all of that information into one place so that analysts with different mission spaces can access that information. And now think about this as hundreds of thousands of just commercial vessels out there. And if you take this down to the rowboat level of objects can go out on the water, estimates in the order of 20 million objects globally, from dhows to rowboats all the way up to super tankers that traverse the globe. So it is a very large problem, and putting all that information together in a meaningful way and taking the data and making it actionable information is the hard part. So what we've done is we've built an ecosystem where that data goes in, and there are complex event processors running that independent analysts can develop their own rules to watch for it on a daily basis. In our unclassified system alone, we're tracking about 450,000 objects daily. So even if you focus down on one small area of the globe, you're still talking about hundreds of tracks it's not practical to investigate each one of them. So we've allowed the operators and analysts to set up their own rules, tripwires, geofence boundaries, ship name lists, other information that they can program into the system so that when those conditions occur, the system tells them it's happened, and they can go further investigate and understand what's going on and apply the gray matter fusion now and their trade expertise to the problem to then help answer the questions of what they're using the system for.
I got decent grades in science class, and I understand that the Earth is, about 70% water. We're talking about millions of data points, but trying to understand how big, what is the scale of the issue here?
So just the unclassified data that we collect on a daily basis is around 400 million positional reports. So we deduplicate some of that information because it's too close in space and time, and for the maritime environment, knowing where something is 3 or 4 seconds later, it hasn't really moved. Even a minute later is probably not very relevant. So we thin that data out, and what we ingest into the system is around 100 million posits daily out of the 400 million that we bring into the front end of the system. Then we thin it out a little bit and deduplicate things. After we process that, those 100 million records get turned into those 450,000 ship tracks. So when you do that, you're getting updates on most of these records. Some voyages will start during the day, so they will go from being off and in port to out and in the ocean. So that becomes a new track that the system is tracking. Some that were out on the open ocean go into port and will turn off their devices, and they will go away from tracking for a few days while they're in port doing their thing. And then other ones are persistent across that time. We have in our system that dates back to 2007 when we were running things. We had ferries in the Med that operated 24/7. We never lost track of them. So we had information on those for years and years and years because they were always broadcasting that information. They were easy to track, but they were good actors. They're not part of the problem. They're part of the solution because you have to understand where all the good guys are in addition to the bad guys and try to sort them out so that you can do that. But from a data scale problem, it's a huge problem, and we bring that data in near real time, process it from our front end where we bring it in, normalize it into a common record format, turn it into XML so we can send it to our various systems and through cross-domain guards to get to higher classification level systems and move it around and get it to those systems and process it within a minute or less.
That is a lot of data to work with. I'm thinking about the scale. I mean, you're mentioning on the low end hundreds of millions of data points. I'm imagining, and I hope I'm right, that it's not all just human actors sifting through all that. Can you help me understand how emerging technology like AI is driving initiatives at NRL to sift through and understand this data in a cohesive way?
So yeah, the data at our front end, right, we normalize it, as I said, and we only bring in maritime relevant data. So we're just not bringing in random internet data like Google would do and do large language models. We're bringing in maritime specific information. So it already has key information in it. And a posit has to have specific things. It has to have a time, has to have a latitude and a longitude. The assumption is it's maritime, so it's happening at or around sea level. So we don't have to worry about that altitude problem so much. So we bring that in, and the first thing that it hits is called Mongoose, which is our data correlator fusion engine. That runs on a large convolutional neural network. In the past, it had large logic, like Boolean rules, if then else type of things that take what we call the correlation parameters, the common parameters. AIS is an easy one. It comes with a MIMSI number, which is a maritime identifier number that is broadcast with the AIS data. So imagine opening a connect the dots book and all of the pages were clear and all you saw was all the dots. So by having that MIMSI, it sort of already pre-sorts as things come in. You know what page it goes on, right? Because it goes on the page for that MIMSI and you time sort them and you can easily put those breadcrumbs together into a comprehensive ship track. So that's the easy side of the problem. What Mongoose also does is it brings in dissimilar data that doesn't have all that information and correlation parameters. It brings in surface track radar. So like a ship's running a radar, we have those on the shore that are looking out and tracking things that are on the water in what are called choke points. We work with Maryland law enforcement that has several sites up and down the Chesapeake that collects both AIS and collects surface radar. So it's tracking things that have AIS and all vessels that are typically made out of metal, so they have a large enough cross-section that they report information back to those, so we're tracking those. So we have to put that information together as well based upon geospatial time constraints. So we know how fast ships move, we know there's biases and errors in all the measurements, and we try to put that together as best we can. So Mongoose does that as well. Now throw into the mix something like a picture from a commercial satellite that's from an overhead system. Do you know what the ship is? Typically you don't. You might have some basic parametrics like what is the length of the ship? What is the width of the ship? If it's color imagery, you might know the color of the ship. You might know a basic category of the ship, like it's a cargo vessel, it's a liquid natural gas tanker, it's a military vessel, right? But these are usually just collected coincidentally with other things that are being taken pictures of near the shoreline, and a ship shows up in it. So what we're doing there is we send those images off to what we call image data conditioners. They chip through this large scene, which is mostly open ocean, and it has to find the ship. So it's sort of like, where's Waldo? And you don't know how many Waldos are in the picture and which Waldo it is. And so it has to do all those things. And then with images, there's confusers. There can be rocks. There can be buoys that are anchored to the bottom of the water that aren't actually out there moving around that show up in the image. There are wave caps near shorelines. There can be wave caps during storms out in the open ocean that are long and white and look like vessel characteristics. There's clouds. There's popcorn clouds. There's cirrus clouds. There's all these things you learned in your science class that an image data conditioner, when it's looking across an image, and this is what imagery analysts have done for years and years and years. We've been working on this in conjunction with all the major organizations that do image collection, is that first part of the problem, which is how do you find the good bits in that picture and focus on them? And then we chip out around that object and we send it along. And we've been doing a lot of work in terms of trying to create labeled data sets, right? Big topic of today is AI ML. So the AI needs a large training data set. So everybody knows you can upload a picture with a cat in it to the internet and it'll find the cat. It could be hiding under a bed, under a blanket, just its eye sticking out. That algorithm will find the cat in the picture. The problem is we don't have millions of pictures of the same vessel under different lighting conditions, different backgrounds, different sea states over time that have been labeled with what they are. And so we don't have those training sets. So we have been taking AIS data, which tells us who it is, and correlating it with imagery that's collected and see if we can get close enough time, spatial distance, and say, we believe that is this same object based upon its length and that it's reporting itself. I always use the good ship Lollipop as my naval reference frame for a ship name. And so if you know how big the good ship Lollipop is and in the picture that all matches, we append a confidence to it. We label that image and say, this is the good ship Lollipop. And we're building up. And we now have a couple of million images total globally for the hundreds of thousands of ship objects that are out there. So if you do the math, we're about 400 million images short of having a good training set to identify these things automatically from commercial or government collected imagery.
Can you help me understand how an initiative like Proteus functions in this ecosystem?
So it functions, we have to go out, and the way NRL works is we're a working capital fund. So we don't get money directly from Congress to solve Navy problems. We have to go to the Navy, to the IC, to the DOD, to the big intel organizations, and look at what their hard problems are and know that we have the expertise and put together pitches to sell to them. So with Proteus, we go and we've been working with those large DOD organizations and more so now with the other federal organizations like Department of Transportation, Department of Commerce, NOAA, that have these tangential, they require knowledge and operating in the maritime domain, but they don't necessarily have all the resources to do that with their own staff or to have the data. So they come to me looking for the data, and we try and build that coalition of the willing to put together enough of these people that need things to fund my team to keep the heartbeat going of the system operating out in the cloud and generating the data and keeping the user interface up and operating and adding new capabilities based upon their requirements into the system. And we've been successful at that for many, many years now.
I hope that continues. Alan, we've talked a lot about the different things that NRL is doing. I just wanted to get your take on some of the trends that you're seeing, whether it's in efficiency, maritime domain awareness, that you're tracking through the end of 2025, the back half of 2025, as well as going into 2026.
So the challenges are recurring challenges because the environment is ever changing. What we're seeing and the bigger challenges coming on now that we're looking at coming up with solutions for in 25, 26 and beyond is proliferation of low Earth orbiting space assets, whether that's through space development agencies, tranches of satellites that they're putting up that are intended to directly support the warfighter, whether it's the intelligence systems that are going up. But we're talking about tens of thousands of satellites now generating information and dealing with that at scale. What we're focusing on is that problem of turning the data into actionable information before it goes into a Proteus system. That's the hard part, because we don't have enough data analysts to look at the images we collect today, let alone a 10,000-fold increase in the number of them. So if we don't get the AI trained, and we're going to have to do that through synthetic imagery generation with realistic scenes so that we don't confuse and create bad models that don't recognize ships. One of the examples somebody gave was, right, they were training the model on looking for military type of vehicles, and part of those vehicles were actual commercial, civilian type of cars, and they ran enough commercial cars through that model that it started confusing military transport vehicles with these cars because the models became oversaturated with data in the wrong way. So it's a fine balance, and that's the large area where we're focusing, because it's going to be an intractable problem when we start generating that much more data that we can't handle. So if we don't start turning that first level of data into information that can go into a system that can be made sense out of by people and other AI beyond that, we're going to be dead in the water and never able to process it. We'll just be saturated with too much information and people not knowing where to start.
Well, I'm hoping to see the ways that you continue to stay afloat in the year. Alan, thank you so much for joining us. I appreciate it.
All right. You're very welcome, Jordan. Thank you.